Hey everyone, welcome back to the channel. In today's video, we're diving deep into one of the most groundbreaking papers in the field of computer vision, AlexNet. This paper, published in 2012, revolutionized the way we think about deep learning and image classification. If you're into machine learning, computer vision, or AI, you're in for a treat. We'll explore the key details of the paper, analyze the architecture, the innovations, and discuss how it changed the AI landscape. So let's get started. Before AlexNet, image classification with deep learning wasn't as popular. In fact, traditional machine learning methods like SVMs and feature extraction techniques were still dominating the field. The general consensus was that deep neural networks, especially convolutional neural networks, CNNs, were not practical for large-scale image classification due to issues like vanishing gradients, overfitting, and computational inefficiencies. But AlexNet changed all of that. Now, we'll talk about the architecture itself. AlexNet is a deep CNN with 8 layers. The first 5 are convolutional layers, and the last 3 are fully connected layers. To make it easier to understand, we're going to break this down layer by layer. In the first layer, the first convolutional layer takes the input image, which is typically 224 into 224 into 3 in size, and applies 96 filters of size 11 into 11 with a stride of 4. This layer is followed by a ReLU activation function. The idea behind using relatively large filters is to capture the most important features from the image early on. Moving on to the second layer, we apply 256 filters of size 5 into 5 with a stride of 1. Again, ReLU is used for nonlinearity. And this layer is followed by max pooling with a 3x3 window and stride 2 to downsample the output. Layer 3, Layer 4, and Layer 5 are similar in structure with increasingly deeper convolutions. Layer 3 uses 384 filters of size 3x3, while Layer 4 and Layer 5 uses 384 and 256 filters respectively. The key idea here is that the deeper the layer, the more abstract the features being captured, with earlier layer detecting edges and textures and deeper layer capturing more complex patterns. The final 3 layers are fully connected. These layers flatten the output of convolutional layers and pass it through the dense layer to make prediction. The last fully connected layer, FC8, has 1000 units corresponding to the 1000 classes in the ImageNet dataset. Now, we'll talk about innovations that made AlexNet so successful. First, it wasn't just about the architecture. It was about how they tackled the challenges that previous models couldn't overcome. A major breakthrough was the use of GPUs for training. Prior to AlexNet, deep learning models were primarily trained on CPU, which was slow for large datasets. AlexNet leveraged 2 GPUs in parallel, reducing training time drastically. This made deep learning models feasible to train on large-scale datasets like ImageNet. AlexNet used the ReLU activation function, which helped mitigate the vanishing gradient problem. Unlike the traditional sigmoid or 10H, ReLU allows the model to train faster by not squashing gradients. AlexNet also introduced local response normalization, a technique that normalizes the activations within a local region, encouraging competition between neurons. While it's not as widely used today at the time, it improved generalization and performance. And to deal with overfitting, the team used data augmentation techniques like random cropping, flipping, and altering color properties. This helped to artificially increase the size of the training dataset, providing more varied examples to train the model on. And dropout, a regularization technique, was applied to the fully connected layers. During training, it randomly deactivates neurons to prevent overfitting. This helped AlexNet generalize better, especially on the ImageNet dataset. First of all, we'll talk about ReLU, or rectified linear unit. Before AlexNet, traditional activation functions like sigmoid or 10H were commonly used. These functions tend to squash their outputs into a narrow range, which can lead to the vanishing gradient problem during backpropagation. This makes it difficult for the model to learn effectively, especially in deeper networks. ReLU is defined as fx is equal to max O to x, meaning it outputs 0 for negative values and retains positive value as is. This simplicity made ReLU a game changer for several reasons. Unlike sigmoid or 10H, ReLU doesn't involve computationally expensive operations like exponentials. And ReLU doesn't squash gradients, enabling the network to propagate large updates back through the layers. And ReLU introduces sparsity in activations as some neurons output 0. This sparsity improves efficiency and reduces dependencies between neurons. By incorporating ReLU in every convolutional and fully connected layer, AlexNet made training faster and more effective compared to the previous architectures. Next, we have local response normalization, or LRN. This is a technique used in AlexNet to improve generalization and encourage competition between neurons. LRN applies normalization within a local region of the feature map. The intuition is to boost activations that are significantly larger than their neighbors while suppressing weaker ones. The key benefits of LRN include enhanced feature detection, which encourages competition among neurons and highlights significant activations. And by normalizing activations, it reduces the risk of overfitting. Although LRN isn't widely used today and has been replaced by batch normalization in most architectures, it was a clever idea for its time and contributed to AlexNet's success. One of the biggest challenges with deep networks is overfitting, especially when training on relatively small datasets. AlexNet tackled this using data augmentation, a technique to artificially increase the size and diversity of the training dataset. Here are some key augmentations used in AlexNet. Random cropping. Instead of training on the fully sized image, AlexNet randomly cropped smaller regions, effectively creating new training samples. The second one is flipping. Horizontal flips were applied to images to simulate variations. And the third one was color alterations. Brightness, contrast, and saturation were altered randomly to make the model robust to different lighting conditions. These techniques ensured that the model wouldn't simply memorize the dataset, but would learn to generalize better. Data augmentation was critical to AlexNet's ability to excel on ImageNet's dataset. Finally, we'll talk about dropout, one of the most influential regularization techniques introduced in AlexNet. Dropout works by randomly dropping out or deactivating neurons during training with a certain probability, typically 0.5 for fully connected layers. Here's how it works. During each training iteration, dropout sets a fraction of neurons to 0, effectively removing them. This forces the network to learn redundant and independent representations, reducing the risk of overfitting. And at this time, all neurons are active, but their weights are scaled down by the dropout probability, ensuring consistent predictions. Dropout was applied to the fully connected layers in AlexNet, making the model robust and significantly reducing overfitting on ImageNet. Today, dropout remains a widely used regularization technique among deep learning models. These four techniques, ReLU, LRN, data augmentation, and dropout, were revolutionary at the time and played a significant role in AlexNet's performance. Together, they allowed the model to overcome the challenges of deep learning and achieve state-of-the-art results. Now, we'll talk about the results. AlexNet was trained on the ImageNet dataset, which consisted over 1 million labeled images. The results were nothing short of spectacular. In the 2012 ImageNet Large-Scale Visual Recognition Challenge, AlexNet achieved a top 5 error rate of 16.4%, significantly outperforming the second-place entry, which had a top 5 error rate of 25.7%. This massive leap proved that deep neural networks could outperform traditional methods when properly trained. AlexNet's impact on the field of AI cannot be overstated. It marked the beginning of the deep learning revolution, inspiring models like VGG, GoogleNet, and ResNet, each building on the principles AlexNet established. The paper's success led to an explosion of research in deep learning, making it the go-to approach for a wide range of problems in computer vision, natural language processing, and beyond. But of course, no model is perfect. AlexNet had its limitation. For one, the model was computationally very expensive, requiring 2 GPUs for training, which wasn't always accessible. Additionally, the architecture itself is considered quite shallow by today's standard, as deeper networks like ResNet have since shown that increasing depth can improve performance even further. To wrap it up, AlexNet was a groundbreaking paper that transformed the deep learning landscape. It demonstrated that deep neural networks could be successfully trained on large datasets using GPUs and introduced several key techniques that are still widely used today. Its success opened the door for rapid advancement of deep learning in both academia and industry. Even though it's been over a decade since its publication, AlexNet's legacy continues to shape the field. If you found this deep dive into AlexNet interesting, make sure to hit that like button and subscribe to the channel for more AI and machine learning content. Also, feel free to drop any questions or comment below and I'll happy to discuss them. Thanks for watching and I'll see you in the next video.